So before we get into these 5.2 notes day 2, I would like to go over the last couple of questions that I skipped yesterday or didn't quite get to. So what we're looking at is, if you just look in your packet on the last day of what we did, and then there's this problem, number 8. Okay. So let's think about how we would do this. I don't want to just tell you. I want, like, as a class, we're going to be able to think through this and figure out. So we don't know how to integrate this just on our own. We can't just do this in our head. So that means we do need to do a u substitution. Now remember, u is not going to be x. It's not going to be the whole thing. It's going to be part of it. And yesterday, what was u most of the time? The denominator. If we do that in this problem, let's see what happens. Okay, what would the du equal? So it would be like 1 times natural log x plus x. Okay, basically more than what I have right here. So this is not the u we want. Okay? It doesn't mean we're totally wrong. It just means we need to modify. So u cannot be the denominator. It didn't work.
Just take ln of x and then for your du.
Okay, so let's let u just be the natural log of x piece. Now we're going to know this is good if our du is in the problem. So what would the du be? 1 over x dx, which is in the problem. It's right here and right there. So although it wasn't totally obvious what we needed to let u equal, we can figure it out. And then we end up just getting a plain old 1 over u du, which we learned yesterday integrates to natural log of u plus c. Don't forget you need absolute value bars there. And then our last step here is to go ahead and write in, okay, what was u supposed to equal? It was supposed to equal natural log of x.
You have an ln of x?
Yeah, so natural log is kind of weird, but you can have it just like how you can have sine of x. It's weird, but it is possible. Okay, so we didn't quite get to that one yesterday, but there it is. All right, now let's look at the next one. So here's 9. And again, thinking about our tools of, like, how did we know what to let u equal? Remember, we had parentheses. There's no parentheses in this problem, though. We had the power on e. That's not an issue here. So our first try to do u, I'm kind of giving you a little hint, that's not going to work out here. So if you're writing in pen, maybe hold off or make sure you're writing in pencil. But if we let u be the denominator, the same thing's going to happen as in the previous problem. Okay, except a little bit different. Not the exact same thing. But what we don't get is a matchup. I have lots of extra stuff up here. Now, normally that would mean Toko, but this would be like crazy, crazy Toko, like we've never seen before. Or we let u be the wrong thing, or we're missing something else. So in a situation like this where you just cannot get u to work, you've got to switch up the problem. You've got to make it look different. Okay, so remember up here, we did this one yesterday. We rewrote the tangent as sine over cosine, and then we were able to figure out the problem. So on 9, we can't really do that, but how do you take a polynomial and divide it by another polynomial? Okay, we could try factoring, and if something cancels, that's great. If nothing cancels, that didn't really help us. What do you think?
You can do the thingy, the trick.
Okay, hold on. Okay, go ahead. Okay, what do you think?
No, I don't think it. I'm just wondering.
Okay.
Since for addition, it doesn't matter the order.
Okay.
Is there any way you can do x squared plus 1 plus x and then have the x squared plus 1 cancel each other?
No.
Not at all.
Because if you think about, I'm going to show why in general, why you can't cancel here. I'm going to show you with numbers. Here's a fraction 5/6. Okay, if I added 2 to the top and the bottom, would that be the same? It's 5/6 the same as 7/8. So whether you're adding 2 or you're canceling 2, it doesn't work that way. The only way we can get around that is by factoring, or what we are going to do, which was a few of you said, long division. Okay? All right. Now, I'm going to remind you how to do long division, and I'm just going to ask that you, for a moment, just say, yeah, I remember I hated this, or I don't know how to do this, or whatever. And just know that you're going to learn it again, and it's not going to be as hard the second time you've learned it, or the third time, or however many times you've seen this. All right? I will tell you that in calculus, we do this a few times, and students always, by the end of the year, not even the end of the year, but by the end of this chapter, they're like, yeah, it's not nearly as bad as I remember it being. Okay? And if you were really good at it last year, that's going to help you. But we're all going to move forward. So the way you do the long division here is you take the denominator and you got to divide it into the numerator. Now, do you guys remember when you wrote stuff like this out, if there was a missing term, what did you do? You put a 0 in. So we're going to go denominator into numerator. Okay. So then, there's 4 basic things. You divide, you multiply, you subtract, and you bring down. Okay, so the first thing is we divide. Sometimes this is going to be an easy step, sometimes it won't be so obvious. How many times does x squared go into x squared? Once. So this one was more obvious than maybe another problem would be. So if you're not sure what should go here, think of it like this. When you multiply 1 times this whole thing, let's go ahead and do that. 1 times x squared, 1 times 0x, and 1 times 1. When you do this, these 2 terms should be the exact same, because our next step is to subtract.
Yes.
All right, and you can either put parentheses. What I kind of like to do is just go ahead and distribute that negative all the way through. If there were already negatives here, we would subtract them and make those positives. So that's the third step, subtract. The first term, the first column, always cancels if you're doing this right. Sometimes other columns cancel as well. So in the middle, positive x minus 0x, that's just an x. And then 1 minus 1, that ends up canceling as well. You can't go another round. 9 times out of 10, if you need to do long division, you're just going to go 1 round. What I mean by a round is you do it 1 time, and then you're left with the remainder here. And the way we write that is we add the remainder over what we were dividing by. Okay, so the whole reason we kind of do this is to make this polynomial divided by a polynomial, we break it up into something more manageable. All right, so we don't have to do this on every problem. I'm going to talk later about how can you recognize when to do it and when not to, when you don't need to. But for now, let's go ahead and just kind of go with what we have. So I'm going to replace my function with this new rewritten function. They're equivalent. They're the exact same. They just look different. It's like a different, same person wearing different clothes. And this whole thing in parentheses is my function. Now, since there are 2 parts, I'm really going to break this up into 2 integrals. And we can even go as far as to writing it as 2 totally separate integrals. I think this makes it easier. It's not required, but I'm going to do it because I think it makes it clear. We do 1 integral, we get the answer. We do another integral, we get the answer. So the first part is actually the easier. What's the antiderivative of 1? 1x. It's like whose derivative is 1? X. All right, now in order to do the second part, this is where we are going to have to do substitution. So let's let u be the denominator. This time, though, it will work out really well because we will have what we need in both places. We have an x dx and an x dx. It matches up. The 2's in the way, so I divide that over. And so we end up getting 1 over u du. So this part of the problem right here is just like what we did yesterday. So we have 1/2 natural log of u. I'm going to go ahead and put plus c since I'm done integrating. And then the last thing we would want to do is instead of u, we would want to go ahead and put in the x squared plus 1. That's your answer. So long division, it's annoying, but it's really only a tiny part of this problem. Unfortunately, it's the first step. Okay, so it's something you really need to be able to do. There's 3 long division ones on your book on this book assignment.
When you expanded the integral, why did you put dx with both terms?
Because it's applying, because dx really is just saying, hey, this is the derivative. So 1 is the derivative, and then we anti-derived. This is also a derivative, we anti-derive.
Okay.
Yeah.
Is there only 3?
There's one more that you could. There are 3 that you have to use long division. There's a 4th that you could do long division, or you could rewrite it a different way.
Okay.
And get out of that. Okay, so there's 3 long divisions. The way you know to do them is if you let u equal the denominator and it doesn't work out, and there's no parentheses or anything, you need to try long division. Typically, it's when the numerator and denominator are the same degree, or where the numerator is even a higher degree. Okay, that's typically where you need to use that. All right, let's go ahead now, and if we have time at the end of class, I'll do another long division problem. But let's go ahead and look at this day 2 stuff. So a lot of this is going to be me saying, hey, we've done this before. What's the first step? And then you guys are going to finish it. And then we'll go over it, okay? So what does it mean to solve a differentiable equation or differential equation? It means this is the derivative. So do you guys remember the prep work we had to do here? Move the dx to the other side and integrate both sides. That's how you get rid of those d's. So we have y equals. Now I'm just going to go ahead and rewrite what we have. And this is exactly what we did yesterday. So I want you guys to try this on your own. All right, so here's the work here. So a couple of mistakes that I know students tend to make. They forget this little negative right here. Okay, this is the derivative of 2 minus x is negative dx, or negative 1 dx. The other thing is they forget that you can put that 3 in the front. You can do that with numbers that are being multiplied or divided. You can't do that with x, you can't do that with trig, but you can do that with just a number you're multiplying or dividing. Sometimes on these differential equations, you have where they give you like x equals 1 when y equals 2, and then you have to go through and solve for c. That happens sometimes. It didn't happen on this, so we're going to move on. All right, example 2. Find capital F. When you see capital F, this could show up a lot more, but it really only shows up one time. And that is when you're given capital F, which is an integral, and you're asked to derive that integral. Does anybody remember the name of this theorem that tells us how to do this? Yep, the second fundamental theorem of calculus. The fundamental theorem just tells us like, hey, when you integrate, plug in your bounds, okay? This one tells us when you're deriving an integral, what to do. This was on your last test, and honestly, it was probably the easiest problem on your whole last test, but only about half of the people got it right. The people who got it wrong made it more complicated than it needed to be. So let me explain this. And capital F is our trigger. This is how we know we need to do this. You're not going to integrate or derive 1 over t. You're not going to integrate or derive that. You're kind of doing both, so they cancel each other out. What you're going to do instead is, in place of t, plug in your upper bound, and then apply chain rule, where you take derivative of the upper bound. Okay, that's half of the problem. Then minus, and then we do the same exact thing with the lower bound. 1 over x times 1. And that's it. These tend to be the easiest problems. The people who get them wrong, they do more work for the wrong answer. Okay, they try to integrate it and then they try to derive that. You could get the right answer that way, but you end up doing a lot of work, lots of chances for a mistake. By the way, this does simplify to 0 if you're just curious or did that. You don't have to though. Okay, I'm going to keep that up on the board, but let's go ahead and move on to example 3. All right, so you guys tell me, how do we find this area?
You need to integrate it.
So we could estimate it using Riemann sums. We can find it exactly by integrating. We need bounds though.
0 and 4.
So 0 and 4. Those, it means start at x equals 0, stop at x equals 4. Those are my limits of integration, the bounds. Okay, so this is like one we did yesterday. So go ahead and try to finish this one on your own. Okay, so a lot of you are done with this one. Did you guys remember to change your bounds?
Yeah.
So if 4 is an x value, what's 4 squared plus 1? 17. What's 0 squared plus 1? 1. The reason I want you to be able to do this, there's a way out of this, but this might be the answer. If it's multiple choice, this could be the answer. And I don't want you to get it wrong because you know how to get the final answer, but you don't know all the steps. So we can do natural log of u. The nice thing about this is I don't have to go back to x. You could go back to x. You could put x squared plus 1 here, but then you're going to have to use the original bounds. So we get natural log of 17. I dropped the absolute value bars because what I'm plugging in is a positive number. This is perfect for a final answer, anything equivalent. Obviously, it does simplify to natural log of 17, which if you used your calculator, comes out to be about 2.8. 2.833. So who knows if this is calculator, non-calculator, multiple choice, free response, these all mean the same thing. Okay? So that's essentially, we've done this area thing before. We just hadn't done it where natural log was in our answer. Okay, let's turn the page and let's talk about some calculator problems. If you don't have your calculator out, go ahead and get that out. A good idea would be to just go ahead and clear things out and maybe even clear your variables. You clear the home screen by doing F1 and then 8 is clear home. And then you clear your variables by doing second F1 clear AZ. A to Z. All right. So example 4 talks about average value. Who remembers the average value formula?
1 over b minus a.
1 over b minus a times the derivative of
You guys are awesome. So if you don't know this, you need to know this. I gave this to you on your last test. That will be the last time. If you're asked to do average value again, you've got to know this formula. It's not really like a formula. You're pretty much just doing 1 over the difference times the integral with these as your starting and stopping point. Okay? Before we continue with like how to get the answer, I do want to mention it told us to use average value, but the reason I really knew to do average is because they are saying average price, and that is P. They're asking us to average that thing. That's average value. If they were asking us to average that thing's rate of change, like what's the average rate of change of price, then that would be an AROC problem. That would be like just a slope. Right? But I know we're doing average value because we're averaging that thing. Now, we're going to take the easy way out if we get to use our calculator. All right, and I'm going to go ahead and just do 1 divided by 10 because that's easier than trying to do the parentheses with the whole 50 minus 40. Remember, we do integration up that way, and we're going to type this in. Please be aware that you need to use parentheses on that 400 plus 3x. We need to go comma x, comma 40, comma 50. So it's the same stuff we had been doing when we typed these in the calculator. If you press enter right now, you probably will get a natural log in the problem, which, you know, the answer choice, that's what it may look like if it's multiple choice. If though you want a decimal, you got to do diamond enter. A good idea to look at your calculator and make sure it looks exactly like what you want it to look like. If you mess up with parentheses, you should be able to figure it out because either you're going to get an error or it's going to spit out to you something that does not look like what you wanted it to look like. And that's usually a parentheses mistake. Say that what? So again, if you're not getting this answer, first of all, check. Make sure that what yours looks like up here looks like your paper.
Mine looks like that. I got like negative 3,000 times natural log of 52 over 55.
Yeah, that's what I got too.
Oh yeah.
But then we said, hey, we probably want a decimal answer
Right.
just because of the context of the problem. So we do diamond enter. Does that answer your question?
Yes. I tried that.
Did you get negative 3,000? But does it say LN in the line?
Yeah.
Okay, so do diamond enter. It's not wrong what you have up here if it's different. Did you use 90,000 or did you possibly do 900,000? You used 40 and 50? I mean, I can look at this, but you probably... Did you do 1/10?
Yes.
Okay.
Do I need to put, oh, wait.
Yeah, so you could divide by 10 at the end, or you could do 1/10. All right. All right, so we got 168. This is a price, so let's go ahead and put a dollar sign. And this is about the only time when you're going to see this rounded to 2 places. It would be fine if you went to 3 because you can't actually have a fraction of a penny. This is probably going to be multiple choice. If you're ever not sure, round to 3, unless it explicitly says something else. Okay, moving on. Last problem of the day. Several parts, but all the same problem. We got a particle. It's moving along the x-axis. They give us velocity, and here's velocity. Remember, we called these problems PVA, or motion, particle motion, but PVA was nice because it went in order. Position, velocity, acceleration. So later on, if they ask us about acceleration, I need to derive. If they ask us about position, I'm going to need to integrate. Okay? So on A, it doesn't really ask us about any of those things. It says which direction. So position, velocity, or acceleration. Which thing tells us the direction of a particle? Velocity, which is what they give us. So we just need to evaluate velocity at 1.5. And you don't have to show the actual typing in of 1.5. You can. You do need to make sure that you're using parentheses wisely. Okay, so at t equals 1.5, the velocity is negative 1.167. So, because the velocity is negative, the particle is moving to the left. And that we can say because v of 1.5, we could say is negative, we could say less than 0. You could say the velocity is negative, but then you have to say at t equals 1.5. So you need all those elements in there, but you can be creative with how you write it out. What if this had said y-axis? How would that change my answer? What direction does the y-axis run? Not left and right. Up and down. So if this said y-axis, how would that change my answer? It would say down. The answer would be down for the same reason. Okay. B. Find the acceleration. So given velocity, find the acceleration at 1.5. How am I going to do this? Find the derivative of velocity at 1.5, and your calculator will do all of these things. Okay, those of you who are really struggling with a lot of the rules in here, you need to get really good at the calculator so that you can get these calculator problems. So I'm going to remind you of how to do this. F3 integrates and differentiates. It just pulls up a little d there. Okay, so then we're going to do, and I'm going to go ahead and use t. Whoops, I cleared that off. I need to put t squared minus 4 in its own set of parentheses. Now, if you just wanted to just find the derivative, find the acceleration expression, we could stop there. If you want to evaluate this at 1.5, there's a few different ways to do that. The way I think you're most comfortable with is storing the value. So we do 1.5 stored in for t, and I'm just using t because that's what the paper says. We could have used x. And then once you've stored 1.5 in, you can either grab the answer or even that. Okay? And that will actually plug in 1.5 in for t for us. So we could have done this by hand, derived it by hand, plugged in 1.5 by hand, and then typed that in the calculator. We could also just do all of the heavy lifting in the calculator. This just takes you getting used to using your calculator for this. So we get 2.778. Right, yeah. There's no units, so don't put them. All right, this next part was something that I really hit you guys hard with in December because this is something that a lot of students get mixed up, but I find that if we go over it again and again and again, then they get better at it. You cannot figure out if a particle's speed is increasing or decreasing based just off of velocity or just off of acceleration. You have to consider both. Does anybody remember? Opposite what? Signs. So this case, the speed would be decreasing because, yeah, v of 1.5 and a of 1.5 have opposite signs. Again, you can explain this a little bit differently, but you got to have all the elements in there. You could have explicitly said the velocity is negative and the acceleration is positive, but then again, you'd have to say at t equals 1.5. Okay, all three of those are stuff that we just did a lot last semester, and it was on your semester exam and all that stuff. Everything after this, these are new things that we haven't done yet. We're going to have to apply what we know about integration to do them. Okay, I'm going to skip D for the time being, and we're going to look at E, and then that should say F. These two things are almost the exact same, displacement and total distance traveled. Okay? The first one is just how far is the particle from where it started. The other one is how far did the particle actually travel. So up here, okay, if I'm talking about distance and I'm given velocity, I know I need to integrate. Okay, it's talking about position, so I got to integrate velocity, which was t squared minus 4 over t. And we are given bounds here, 1 to 2. Now, this will find the total displacement. This will account for moving right, moving left, net change, basically. Okay, so if I go ahead and I'm going to clear my variables because I want to use t again, although I could use any other letter. F3, integrate. And I could have tried to copy and paste, but I'm just going to retype it in. Okay, after your comma t, don't forget your bounds, comma 1, comma 2. It gives you, again, an answer with natural log in it, so you could do a diamond enter if you really wanted a decimal answer, which, honestly, it doesn't really matter. If your answer's right, you're good. So this means the particle is 1.273 meters, centimeters, whatever it may be, to the left of where it started. The net change was this to the left. It doesn't mean that that's how far it traveled. It could have gone to the right, to the left, back to the right, back to the left again. This is talking about net displacement, which are actually not going to be asked most of the time, okay? I just did it to kind of show you the difference here. Negative 1.273. Okay, so when this says total distance traveled, it's actually very similar, but the only difference is you have got to realize it does not want you to be adding and subtracting. You're just adding. You don't want any velocities to be negative, because it doesn't matter that you're going in the opposite direction, it's still traveling. So the way we take care of that is by absolute value bars. In your calculator, this looks like ABS. Let me write that a little bit better. For absolute value, and then it'll use parentheses. So let me show you how this looks. And what I'm going to do is I'm going to just copy and paste the one we have. I'm going to go ahead and put a parenthesis at the end, and then at the beginning, I'm going to go to catalog. ABS should be at the top. If not, it's because somebody at some point went to the catalog and found something else, so you can scroll up or do alpha or whatever. So notice that the absolute value parenthesis starts and ends at the end. If you mess up with these parentheses, you're going to be able to figure it out pretty quickly because it either will give you an error or it won't look right. Now I want you to notice something here. The answer was negative and now it's positive. It's not always going to happen where you can just make the negative become positive. All right, you got to do the absolute value bars because you don't know when the particle is moving left, right, whatever. So you go to catalog, ABS, and just make sure you open and close the parentheses around the function. This is the first time we've talked about this today, so it's mostly just to kind of get you some exposure to it. We will go over this more at a later time.